In this video, I'm going to go through tutorial questions 1.2 on mole concept. So this will be the part 1, so until the empirical formula and the molecular formula. And I won't go through all the questions. I will only go through the questions asked by the students. So that would be question number 2, question number 4, question number 5, D and E, question number 6, question number 7, question number 8, question number 9, question number 10C, and question number 11. Just to take note that some of my answers are slightly different from the answers given in the tutorial book because I use the reason constant, the one that you all have, in producing the answer, while the answer given in the tutorial book using the all versions of constant. Therefore, the answer in the tutorial book is slightly different from my answer. First, we look at question number 2. Question number 2 given the relative atomic mass of element Y is 32 and asks us to calculate what is the mass of one atom Y in gram. Previously in my video on mole concept, I already told you that the relative atomic mass, and molar mass, they're all having the same numerical value. So in this question, given the relative atomic mass for element Y is 32, therefore the molar mass of Y atoms will be 32 gram per mole. We know that molar mass is for 1 mole of atom Y. So 1 mole of atom Y basically consists of 6.02 times 10 to the power of 23 Y atoms. And the mass of this 1 mole of atom Y is equal to 32 gram. And now the questions want us to find only one atom Y. And what is its mass in gram? So mathematically, we can do cross multiplying. To find X, diagonally, we multiply. So it's 1 Y atom multiplied by 32 gram. And then we divide. So we divide with 6.02 times 10 to the power of 23 Y atoms. So Y atoms we can cancel out to give us the mass of 1 Y atom as 5.316 times 10 to the power of negative 23 gram. Now we move on to look at question number 4. If you have watched my mole concept video, you should know that for this question, only require 3 steps to solve it. Why 3 steps? Because we have been given ethanoic acid, asked for oxygen atoms. So given A, asked for B. Therefore, 3 steps to solve it. So step number 1, we need to find the number of moles of A. So we have been given A, ethanoic acid, 5.7 times 10 to the power of 21 molecules. So means that in step number 1, we need to find the number of moles of ethanoic acid molecules. So which formula to use? We need to use number of particles divided by Avogadro constant, and the number of particles given is 5.7 times 10 to the power of 21 molecules, and the Avogadro constant is 6.02 times 10 to the power of 23 per mole. So that will give us the number of moles of ethanoic acid as 9.468 times 10 to the power of negative 3 mole of ethanoic acid. And step number 2, we do the stoichiometric comparison to know the stoichiometric relationship between ethanoic acid molecule and oxygen atoms. And from the ethanoic acid molecule, the molecular formula, we can see that in 1 mole of ethanoic acid molecule, it consists of 2 mole of oxygen. So that is the stoichiometric relationship between ethanoic acid and oxygen atom. So in 1 mole of ethanoic acid molecule, it consists of 2 moles of oxygen atoms. But now we only have 9.468 times 10 to the power of negative 3 mole of ethanoic acid, and we want to find that is equivalent to how many moles of oxygen. To do this mathematically, again, we can do cross multiplying. To find X, we do cross multiplying, so means that it's 9.468 times 10 to the power of negative 3 mole of ethanoic acid multiplied by 2 moles of oxygen, and then divide by 1 mole of ethanoic acid. and that should give us 0.01894 moles of oxygen. So in step number 2, based on the stoichiometric relationship, we can get the number of moles of B, our oxygen. And then in step number 3, we then can use the formula to find the number of oxygen atoms in the sample. So which formula to use? Again, we have number of mole. We want to find the number of oxygen atoms, and we know Avogadro constant. So again, it's the same formula, but now we are finding for the oxygen atoms. We want to find the number of oxygen atom. We have the number of moles of oxygen, which is this. So 0.01894 mole of oxygen. And we want to find the number of oxygen atoms. And the Avogadro constant is 6.02 times 10 to the power of 23 per mole. So per mole and mole can cancel out to give us the number of oxygen atoms as 1.14 times 10 to the power of 22 oxygen atoms. We move on to look at question number 5D. Again, for question number 5D, we can solve these questions in 3 steps because we are being given quinine, asked for hydrogen atoms. So given A, asked for B. So step number 1, based on what is being given to us, the mass of quinine sample, we then can find the number of moles of quinine. To find the number of moles of quinine, we use the formula mass divided by molar mass of quinine, 324 gram per mole. And that should give us the number of moles of quinine as 3.333 times 10 to the power of -3 moles of quinine. Then in step number 2, we need to find what is the stoichiometric relationship between quinine and also hydrogen atoms. So we know that from the chemical formula of quinine, that 1 mole of quinine consists of 24 moles of hydrogen. So 1 mole of quinine molecule consists of 24 moles of hydrogen atoms. So that is the stoichiometric relationship between quinine and hydrogen atoms. So 1 mole of quinine molecule consists of 24 moles of hydrogen atoms. And now we have 3.333 times 10 to the power of -3 mole of quinine. And that is equivalent to X mole of hydrogen. So how do we find X? Basically, we can use cross multiplying. Cross multiply, so 3.333 times 10 to the power of -3 mole of quinine. Multiply by 24 mole of hydrogen. Divide by 1 mole of quinine. Mole of quinine can cancel out to give us 0.08 mole of hydrogen. And in step number 3, we want to find the number of hydrogen atoms. We already have the number of moles of hydrogen atom. We want to find the number of hydrogen atoms. So which formula to use? We can use the number of moles equals to number of particles divided by Avogadro constant to find the number of hydrogen atom. So the number of moles of hydrogen atom we have equals to the number of particles. The particles here is hydrogen atoms. Divided by the Avogadro constant, 6.02 times 10 to the power of 23 per mole. Per mole and mole can cancel out to give us number of hydrogen atoms as 4.816 times 10 to the power of 22 atoms of hydrogen or hydrogen atoms. Question number 5E also required 3 steps to solve this question because we are being given quinine A and asked for carbon atoms B. So again, step number 1, we need to find the number of moles of quinine since we are being given the information's mass of quinine. Again, to find the moles of quinine, we use the formula mass divided by molar mass of quinine. to give us the moles of quinine, 3.333 times 10 to the power of negative 3 mole of quinine. And then in step number 2, we need to find what is the stoichiometric relationship between quinine and carbon atoms. And we know that quinine, 1 mole of quinine molecule consists of 20 moles of carbon. So that is the stoichiometric relationship between quinine and carbon atoms. 1 mole of quinine consists of 20 moles of carbon atoms. So 1 mole of quinine consists of 20 mole of carbon. Now we only have 3.333 times 10 to the power of negative 3 moles of quinine, and that is equivalent to x moles of carbon. So how do we find x? Again, cross, we multiply. So 3.333 times 10 to the power of negative 3 mole of quinine multiply by 20 mole of carbon, and then divide by 1 mole of quinine, and the mole of quinine can cancel out to give us 0.06667 mole of carbon. After we have found the moles of carbon, then we can move on to step number 3. So step number 3, we want to find the mass of carbon atoms in gram. So which formula to use to find the mass of carbon? Again, is the number of mole, but now it's the number of moles of carbon equals to mass of carbon divided by the molar mass of carbon, which is 12 gram per mole. Mole and per mole can cancel out to give us the mass of carbon equals to 0.8000 gram. Question number 6, basically given 2 unrelated compounds. One is nitrogen gas and another one is methane. Since they are not related, we need to solve them separately. For nitrogen, we have been given the mass of nitrogen gas. So mass of nitrogen gas, we have been given 8 gram. And we have been asked about the volume of the gas. Since we have been given nitrogen gas mass, and then asked about volume of nitrogen gas, so it's given A, asked for A. So 2 steps to calculate what is the volume of nitrogen gas. So step number 1, again, we need to find the number of moles. Since we have been given the mass of nitrogen gas, so we use the formula mass divided by molar mass of nitrogen gas. That should give us 0.2857 mole of nitrogen gas. And in step number 2, we want to find volume of nitrogen gas. And given, so the question do not give us the conditions, so we can assume it is room condition. So if room condition, the molar volume at room condition is 24 dm cubed per mole. So we can assume it's room condition, since not given the condition. So to find the volume of nitrogen gas at room condition, basically we just need to use the formula number of moles equals to volume of gas divided by molar volume. So to find the volume of nitrogen gas, so we use the number of mole of nitrogen gas multiplied by the molar volume. Per mole and mole can cancel out to give us the volume of nitrogen gas, which is 6.857 dm cubed. And then we can use this volume of nitrogen gas to solve for methane, because the question says the volume of the methane gas occupied by the methane gas is same with the volume occupied by the nitrogen gas at the same condition. So therefore, the volume of methane gas is 6.857 dm cubed under room condition. And now we want to find the mass of methane gas. And again, this one is given A, asked for A. Therefore, we can solve it in 2 steps. So step number 1, since we are being given the volume of gas, therefore we need to find the number of mole of methane gas by using the formula volume of gas divided by molar volume, so room condition, and that should give us 0.2857 mole of methane gas. And in step number 2, since we want to find the mass, so to find the mass of methane gas, we just need to use the formula number of moles multiplied by the molar mass of methane gas, which is 16 gram per mole, to give us the mass of methane as 4.571 gram. For question number 7, it is also 3 steps to solve this question because we are being given H2O2 hydrogen peroxide, but we want to find for oxygen gas. So given A, ask for B. So step number 1, we need to find the number of moles of the one that is being given, which is hydrogen peroxide, H2O2. So we are being given molarity and also volume of solution. So means that we need to use this formula because only this formula is for the solution. So to find the number of moles of hydrogen peroxide, molarity 2 molar multiplied by volume of solution in liter, that will be 250 ml divided by 1000, so giving us 0.250 liter, and that should give us 0.500 mole of hydrogen peroxide. So that is step number 1. Step number 2, we want to find what is the stoichiometric relationship between hydrogen peroxide and oxygen. So since this is a chemical reaction, because we have the chemical equation, therefore we need to find their stoichiometric relationship in the chemical equation. And from the chemical equation, we can see that 2 mole of hydrogen peroxide decompose, it will produce 1 mole of oxygen gas. So that is the stoichiometric relationship between hydrogen peroxide and oxygen given in the chemical equation. So 2 moles of hydrogen peroxide will produce 1 mole of oxygen. Now we only have 0.5 mole of hydrogen peroxide reacting. That will give us X mole of oxygen gas being produced. How do we find the X mole? Again, mathematically, we do cross multiplying. 0.5 mole of hydrogen peroxide multiplied by 1 mole of oxygen, and then divide by 2 moles of hydrogen peroxide. So that should give us 0.250 mole of oxygen, since the mole of hydrogen peroxide is being cancelled out. Then we can move on to step number 3 to find the volume of oxygen gas released at STP. So at STP, we know that the molar volume at STP is 22.4 dm³ per mole. And to find the volume of oxygen gas, we need to use this formula to find the volume of oxygen gas. And from the formula, we know that to find the volume of oxygen gas, we need to use number of moles of oxygen gas that we found in step number 2, multiplied by molar volume at STP, which is 22.4 dm³ per mole, to give us the volume of oxygen gas as 5.600 dm³. Question number 8 also involves 3 steps because given the volume of ammonia gas and asked us to calculate the number of water molecules. So again, given A, ask for B. To do this, step number 1, we calculate the number of moles of A, the number of moles of ammonia gas. So for this, we are being given volume of gas. Therefore, to find the number of moles of ammonia gas, we need to use the formula number of moles equals to volume of gas divided by molar volume. Be careful, we are being given here 72 ml of ammonia gas. We know that molar volume at room condition is 24 dm³ per mole. In order for volume of gas to be able to be divided with molar volume, their unit must be consistent, but here is ml and this is dm3. And we know that 1 ml is equal to 1 cm3. Therefore, 72 ml is equivalent to 72 cm3. But in order to divide with molar volume 24 dm3 per mole, the 72 cm3 need to be divided by 1000 to convert it to 0.072 dm3, so that it can be divided with the molar volume 24 dm3 per mole to give us the number of moles of ammonia. So we get 0.072 dm3 of ammonia gas divided by the molar volume at room conditions 24 dm3 per mole to give us the number of moles of ammonia as 3 times 10 to the power of -3 mole of ammonia. Step number 2, we need to find the stoichiometric relationship between ammonia and water. And we know that the stoichiometric relationship is written in the balanced chemical equation. From the balanced chemical equation, we can see that 4 mole of ammonia will produce 6 mole of water molecules. So that is the stoichiometric relationship between ammonia and water molecule given in the balanced chemical equation. So 4 mole of ammonia produce 6 moles of water. But now we only have 3 times 10 to the power of -3 moles of ammonia, and that is equivalent to x moles of water. So how do we find the x mole of water? Again, mathematically, we do cross multiply. So 3 times 10 to the power of -3 mole of ammonia multiplied by 6 mole of water divide by 4 moles of ammonia, and the mole of ammonia we can cancel out to give us 4.50 times 10 to the power of -3 mole of water. After we get the moles of ammonia in step number 2, then we can move on to step number 3 to find the number of water molecules. For this, we need to use the formula number of moles equals to number of particles divided by Avogadro constant. Now we want to find the number of particles, number of water molecules. Therefore, we need to multiply the number of moles of water with the Avogadro constant. So number of moles of water, 4.5 times 10 to the power of -3 mole, multiplied by Avogadro constant, 6.02 times 10 to the power of 23 per mole. And that will give us 2.709 times 10 to the power of 21 water molecules. Question number 9a is also 3-step question because given mass of copper sulfide 14 gram and ask for molecules of oxygen gas. Again, given A, ask for B. So step number 1, we need to find the number of moles of copper sulfide because given the mass of copper sulfide, so that is 14 gram divided by the molar mass of copper sulfide, that is 159.3 gram per mole to give us the number of moles of copper sulfide as 0.08788 mole of copper sulfide. Then in step number 2, we can see that from the balanced chemical equation, 2 mole copper sulfide will react with 3 moles of oxygen gas. So that is their stoichiometric relationship given in the balanced chemical equation. So 2 moles of copper sulfide will react with 3 moles of oxygen gas. And now we have 0.08788 mole of copper sulfide, and that is equivalent to x moles of oxygen. To find the x moles of oxygen, again we do cross multiplying. 0.08788 moles of copper sulfide multiplied by 3 moles of oxygen divide by 2 moles of copper sulfide, and mole of copper sulfide we can cancel out to give us the numbers of moles of oxygen as 0.1318 mole of oxygen. And then in step number 3, we want to find the number of oxygen molecules. To find this, we can use the formula number of moles equals to number of particles, and the particles here is the oxygen molecules divided with the Avogadro constant. So to find the number of oxygen molecules, basically we use this formula. So number of moles of oxygen multiplied by the Avogadro constant. So the number of moles of oxygen 0.1318 mole multiplied by Avogadro constant 6.02 times 10 to the power of 23 per mole. The mole and mole cancel out to give us the number of oxygen molecules as 7.936 times 10 to the power of 22 oxygen molecules. Question 9b is also 3-step because, again, given the mass of copper sulfide, so this is A, and then ask for sulfur dioxide gas, so this is B. So given A, ask for B, so 3 steps to solve this problem. So again, step number 1, we calculate the number of moles of copper sulfide. So we use the formula mass divided by the molar mass to give us the number of moles of copper sulfide as 0.08788 mole. And then step number 2, we need to find the stoichiometric relationship between copper sulfide and sulfur dioxide gas. So from the balanced chemical equation, we can see that 2 mole of copper sulfide will produce 2 moles of sulfur dioxide gas. So that is the stoichiometric relationship between copper sulfide and sulfur dioxide gas given in the balanced chemical equation. So 2 mole of copper sulfide equivalent to 2 mole of sulfur dioxide gas, because produce 2 moles of sulfur dioxide gas. But now we only have 0.08788 mole of copper sulfide, so that is equivalent to X mole of sulfur dioxide gas that is being produced. So how do we find this X mole of sulfur dioxide gas? Basically, we do cross multiplying 0.08788 mole of copper sulfide multiplied by 2 moles of sulfur dioxide divide by 2 moles of copper sulfide. Mole of copper sulfide can cancel out, so 2 and 2 can cancel out to give us 0.08788 mole of sulfur dioxide gas. And in step number 3, we want to calculate the mass of sulfur dioxide gas, so we need to use this formula number of moles equals to mass divided by molar mass. So to calculate the mass of sulfur dioxide gas, so basically we need to use the number of moles of sulfur dioxide gas 0.08788 mole multiplied by the molar mass of sulfur dioxide, so that is 64.1 gram per mole. So per mole and mole can cancel out to give us the mass of sulfur dioxide as 5.633 gram. Question number 9c is also 3 steps question because given the mass of copper sulfide 14 gram, and then ask for volume of sulfur dioxide gas. So given A, copper sulfide, ask for B, sulfur dioxide. Therefore, 3 steps to solve this question. So step number 1, we need to find the number of mole of copper sulfide because given the mass of copper sulfide, so we use the formula mass divided by molar mass of copper sulfide to find the number of moles of copper sulfide as 0.08788 mole of copper sulfide. And then in step number 2, we find the stoichiometric relationship between copper sulfide and sulfur dioxide in the balanced chemical equation. From the balanced chemical equations, we can see that 2 moles of copper sulfide produce 2 moles of sulfur dioxide. Therefore, we can write in step number 2, 2 moles of copper sulfide produce 2 moles of sulfur dioxide. But now we only have 0.08788 mole of copper sulfide, and that is equivalent to X moles of sulfur dioxide. To find the S mole of sulfur dioxide, basically we do cross multiplying 0.08788 mole of copper sulfide multiplied by 2 moles of sulfur dioxide divide by 2 moles of copper sulfide. Mole of copper sulfide can cancel out, the 2 moles can cancel, the 2 can cancel out, and that shall give us 0.08788 mole of sulfur dioxide. Then we can move on to step number 3 to find the volume of sulfur dioxide gas. We need to use the formula number of moles equals to volume of gas divided by molar volume. So to find the volume of gas, so number of moles of the sulfur dioxide gas multiplied by the molar volume at STP. So that is 0.08788 mole of sulfur dioxide multiplied by the molar volume at STP, which is 22.4 dm³ per mole, to give us the volume of sulfur dioxide gas as 1.969 dm³. Question number 10, I will discuss 10C since students only ask for 10C. So for 10C, we have been given the mass of the hydrocarbon compound and also been given the volume of the hydrocarbon gas compound at STP, and we have been asked to determine the molar mass of the hydrocarbon. So for this question, basically it's just two-step question because we have been given A, the volume of gas of the hydrocarbon and the mass of the hydrocarbon, and we are being asked to determine the molar mass of the hydrocarbon. So given A, ask for A, so it's just two-step question. So step number 1, we still find the number of moles of the hydrocarbon compound. But for this question, we are being given mass and also the volume of the gas. Which one we should use to calculate the number of moles of hydrocarbon? So very obvious, we cannot use the mass to find the number of moles. Why? Because we do not have the molar mass. Remember, the question asked us to find the molar mass. So we do not have the molar mass of the hydrocarbon. So therefore, we cannot use the formula number of moles equals to mass divided by molar mass to give us the number of moles of the hydrocarbon. So in other words, we need to use another formula, number of moles equals to volume of gas divided by molar volume to find the number of moles of hydrocarbon. And we know that molar volume at STP is 22.4 dm³ per mole. And in order to use this formula, the volume of gas must be consistent with the molar volume unit. So in order to make it consistent, we must know that this 100 ml is equivalent to 100 cm³. And for cm³, to change to dm³, it need to be divided by 1000. And that should give us the volume of the gas equal to 0.100 dm³. And divide by the molar volume at STP, 22.4 dm³ per mole. And that should give us 4.464 times 10 to the power of -3 mole of hydrocarbon. And in step number 2, we want to find molar mass. So we have the mass and we have number of mole. So means that we can use the formula number of moles equals to mass divided by molar mass to find the molar mass of the hydrocarbon. So to find the molar mass of the hydrocarbons, basically the mass of the substance 0.25 gram, we divide it with the number of moles, 4.464 times 10 to the power of -3 mole, to give us the molar mass of the hydrocarbon as 56 gram per mole. So this is the first part of the question. We use the two-step to find the molar mass of the hydrocarbon. Now we move on to look at the second part of the question, determine the molecular formula of the hydrocarbon. To determine the molecular formula, we need to calculate the whole number multiple n. To calculate the whole number multiple n, it is equal to the molar mass of a substance divided by the empirical formula mass. Previously, we have found that the molar mass of this hydrocarbon is 56 gram per mole. And from question 10b, we know that the empirical formula for this compound is CH2. Therefore, the empirical formula mass will be 12 plus 2 times 1 gram per mole. And gram per mole we can cancel out to give us the whole number multiple n as 4. Therefore, the molecular formula for the hydrocarbon, which is equal to empirical formula with subscript n, the whole number multiple, and we know that from 10b the empirical formula is CH2, and then the n The whole number multiple we already determined to be 4. So 4, and this gives us the molecular formula for the hydrocarbon as C4H8. Question number 11 is to find the empirical formula and molecular formula of a compound using combustion analysis. So from the question, we know that the compound consists of carbon and hydrogen. And when it is being combusted with oxygen, the carbon react with oxygen, produce the carbon dioxide. And the carbon dioxide produced having the mass of 0.512 gram. And the hydrogen in the element, when combusted with oxygen, it will produce steam or water with the mass of 0.209 gram. So if we want to find the empirical formula for the compound, we need to know the mass of the carbon and the mass of the hydrogen that present in the compound. How do we get the mass of the carbon and the mass of hydrogen? So we can get the mass of carbon from the mass of the carbon dioxide by using the formula mass of carbon equals to the molar mass of the carbon, which is 12 gram per mole, divided by molar mass of carbon dioxide, which is 44 gram per mole, multiplied by the mass of the carbon dioxide produced to give us the mass of carbon as 0.1396 gram. While for the mass of hydrogen, also the same thing, we can determine the mass of hydrogen from the mass of water produced. So to find the mass of hydrogen, we use the molar mass of hydrogen, 1 gram per mole. But in one water molecule, there are 2 hydrogen atoms. Therefore, here we need to multiply by 2 because in 1 mole of water molecule, there are 2 moles of hydrogen. Therefore, we need to multiply by 2. And then divide by the molar mass of water, which is 18 gram per mole, multiplied by the mass of water, 0.209 gram, to give us the mass of hydrogen as 0.02322 gram. After we get the mass of each element present in the compound, then we can construct the table to determine the empirical formula. So the first row is element. So there are only 2 elements present in this compound, which is carbon and hydrogen. And the second row, we fill in the mass. So for carbon, the mass is 0.1396 gram, and the mass of hydrogen is 0.02322 gram. And then we can calculate the number of moles for each element. So mass divided by molar mass. For carbon, 12 gram per mole. That will give us the number of mole of carbon as 0.01163 mole. And the mole of hydrogen, also the same thing. Mass divided by molar mass. And that will give us 0.02322 mole of hydrogen. And then we can calculate the ratio. So the ratio, we need to divide the mole with the smallest mole. The smallest mole is this one. So 0.01163 divided by 0.01163 to give us 1. And then for the hydrogen, 0.02322 divided by 0.01163, and that should give us 1.996. We want the simplest whole number ratio because empirical formula is defined as the simplest whole number ratio of atoms of each element present in the compound. To get the simplest whole number ratio, the carbon simplest whole number ratio is 1, and for hydrogen, because this is 0.004 difference, so we can also round it out to 2 to give us the empirical formula for the compound as CH2. Then we can move on to find the molecular formula for the compound. For the molecular formula of the compound, so we need to use the molar mass. So there's a mistake on the molar mass of the compound. The molar mass of the compound is actually 112 gram per mole. So you can make the corrections in your own tutorial book. To determine the molecular formula, first we need to find the whole number multiple n. using the formula molar mass divided by the empirical formula mass. Molar mass of the compound is 112 gram per mole. And for the empirical formula mass, we know that the empirical formula of the compound is CH2. So therefore, the empirical formula mass will be 12 plus 1 times 2 gram per mole. Gram per mole can cancel out, and that should give us N equals to 8. And therefore, the molecular formula of the compound, which is equal to the empirical formula with subscript n, and the n here is the whole number multiple n. So empirical formula is CH2 and the n is 8. So that gives us the molecular formula for the compound as C8H16.